Hello and welcome to the Deep Dive, where we take your sources and extract the most important nuggets of knowledge and insight. Today we're tackling a really crucial topic in the world of predictive analytics. How do we truly know if our models are any good? You see, the central challenge isn't just building amazing predictors and classifiers. It's about, well, evaluating those predictions reliably. The ideal scenario, of course, is to use new independent data. But let's be honest, that's often just not available. And why relying on the data a model already saw its training data is such a trap, leading to overly optimistic, even misleading results.
That's exactly right. Relying solely on that training error, it can dramatically underestimate a model's true performance out in the real world. What's fascinating here, though, is that the solution often lies in being clever with the data we do have. We're talking about resampling methods specifically, two powerful techniques, cross-validation and the bootstrap. Our mission today is to understand how these methods allow us to accurately evaluate model performance, get a good estimate of that test set prediction error, and even quantify the uncertainty of our parameter estimates, all using the existing data we have on hand. It's really about getting more information from what we already possess.
Okay, so let's unpack this first. The fundamental difference between training error and test error. Why is getting this distinction right so important? What's the biggest risk if we get it wrong?
That's an excellent question because the distinction is absolutely critical. Think of test error as the average error a model makes on new, unseen observations data it has never, ever encountered before. This is what we ultimately care about, right? Is how well the model performs when you actually deploy it. In contrast, training error is simply the error calculated on the observations used to train the model. It's like the model's performance on its homework.
Okay.
And why does training error always look better? Well, because the model has already learned from that specific data. It's like taking the same exam twice. You're probably going to score higher the second time.
Mm-hmm.
This makes training error a really unreliable gauge for real-world performance, as models inherently perform better on data they've already seen.
Right.
We can illustrate this with the concept of model complexity. If you imagine a graph, horizontal axis is how complex your model is, simple line, or maybe a super wiggly complex curve. The vertical axis is prediction error. Now, a very simple model, low complexity, it'll have high training error and high test error. It's underfitting, it's just not capturing the real patterns.
Yeah.
But as the model gets more complex, the training error, that just keeps going down. It's getting better at fitting the data it saw.
Oh, okay.
However, the test error, that's the crucial one, maybe think of it as a red line on the graph. It decreases for a bit, hits a kind of sweet spot, and then actually starts increasing again.
So it's getting too clever for its own good on the training data. Like it starts memorizing the noise instead of the actual signal.
Precisely. That's overfitting. The model becomes overly tailored to the specific quirks and noise in the training data, and because of that, it fails to generalize to new, unseen observations. This whole relationship perfectly captures the bias-variance trade-off.
Okay, explain that a bit more.
So on the left side of our complexity curve, with those simple models, we have high bias. The model is just fundamentally missing the true structure. It's consistently off. But on the right side, with the really complex models, we get high variance. The model is super sensitive to the specific training data it happened to see. It fits the noise, basically. So its predictions jump around a lot depending on the training set, and it performs poorly on new data.
So the best model isn't necessarily the one that aces the training data.
Exactly. It's often counterintuitive. Sometimes you actually want a little less performance on the training data to get better performance out in the wild. The optimal complexity is where that test error curve hits its minimum, finding that sweet spot, balancing bias and variance.
Okay.
And, speaking of understanding error, when we talk test error, we often use metrics like mean squared error for numbers or misclassification rate for categories. But it's also helpful to quickly touch on precision and accuracy, especially in regression. Precision is about consistency. Are your predictions tightly clustered together? Accuracy is about how close they are to the true values, on average. You could have a model that's highly precise, but always wrong by the same amount. High precision, low accuracy. That's bias.
Like always predicting 10 degrees too cold.
Exactly. Or you could have low precision, but high accuracy predictions are all over the place, but they average out to the right value.
Right. Ideally, you want both.
Ideally, yes. High precision, high accuracy, consistent and valid. Different error metrics just give us different views on performance.
So the goal is clear. Minimize that test error, understand its nature. We need models that generalize. But without a fresh pile of new data, how do we get a truly reliable estimate?
Yeah.
That's where these resampling methods come in, right? They give us a window into that test error.
Exactly. We need to cleverly simulate getting new data without actually having it.
So one of the simplest ideas, maybe the first thing you think of, is the validation set approach. Just split the data once. Part for training, part for testing. Done.
Yeah, it sounds intuitive, and it's definitely a starting point.
Yeah.
The process is just like you said. Randomly divide your data into two chunks, a training set and a validation or holdout set. You fit your model using only the training set. Then you use that model to predict on the validation set. The error you calculate there, MSE, misclassification rate, whatever, that's your estimate of the test error.
That's
Seems
right.
simple enough.
I sense a but coming.
But yeah, there are some pretty big drawbacks. The first one is high variability, meaning the error estimate you get, it really, really depends on which specific data points happened to land in the training set versus the validation set. Run the split again, randomly,
Yeah.
you could get a pretty different error estimate. It's kind of shaky, like flipping a coin just once or twice.
Okay. Unstable. What up?
The other issue is potential overestimation of the test error.
Why is that?
Because you're training the model on less data, only the training part, not the whole data set you have, and generally more data leads to better models, lower error. So by training on a smaller subset, the model might just perform worse, making your error estimate higher than it would be for a model trained on all your data.
Right. That makes sense. It really shows how simple intuitions can sometimes lead you astray in analytics. Clearly, we need something more sophisticated, something more stable, more reliable, that uses our data better. This is where cross-validation comes in.
Indeed. It's often considered the gold standard for exactly this reason.
Okay, here's where it gets really interesting then. K-fold cross-validation. You hear it called the workhorse of test error estimation all the time. It's used to pick the best model, get a solid idea of test error. So what does it actually do? How does it manage to be so much more robust than that single split?
K-fold cross-validation is a really elegant way around that variability problem of a simple validation set. The core idea is you randomly divide your data into K roughly equal size parts. We call these folds.
It cuts, like how many?
Yeah, a common choice for K is often 5 or 10. These numbers tend to provide a good balance, a good trade-off between bias and variance in the error estimate itself.
Okay, 5 or 10 folds. Then what?
Then you systematically go through each of these K-folds. In the first round, you hold out fold number 1. You fit your model using the data from the other K1 folds, so folds 2 through K all combined.
Okay, train on most of it.
Right. Once that model is trained, you use it to make predictions on the data in fold 1, the part you held out, and you calculate the error just for that fold.
Got it.
Then you repeat the whole thing, hold out fold 2, train on folds 1, 3 through K, test on fold 2, and so on for all K folds.
So every single data point gets to be in the test set exactly once.
Exactly. Each fold serves as the validation set precisely one time. Finally, you combine the results. Typically, you just average the error rates you calculated for each of the K folds. That average is your overall cross-validation error estimate.
Ah, I see. So averaging across those K trials smooths things out.
Precisely. It's much more stable and reliable than a single validation split. It reduces the impact of exactly how the data got divided up. And just quickly, there's a special case called leave one out cross-validation, or LOOCV. That's where K is equal to N, the total number of data points.
So you hold out just one data point at a time.
Yep, you train on N1 points, test on the one left out, and repeat N times. It has very low bias because you're training on almost all the data each time. But the downside is that the N estimates you get are highly correlated with each other, which can paradoxically lead to high variance in the final averaged estimate. Plus, it can be computationally very expensive if N is large.
So K5 or K10 is usually the better practical choice.
Generally, yes. It hits a better sweet spot in that bias variance trade-off for the error estimate itself. You know, if we look at examples like the Autodata Revisited one in the sources, comparing linear models to more complex polynomial ones, we can see that tenfold CV and even LOOCV error estimates, they tend to track the true test mean squared error curve quite well. They capture the U-shape, finding that minimum error point. They might slightly overestimate or underestimate sometimes, but they give a far more trustworthy picture than a single split.
Okay, yeah, this iterative process, it really seems to tackle that variability head on. It gives us a much more robust picture of how our model will likely perform on genuinely new data. It's like running multiple mini experiments instead of just one big one.
That's a great analogy. It leverages your existing data much more effectively to simulate that unseen scenario over and over.
Okay, now this next part feels absolutely vital. You mentioned it's a common pitfall, and it sounds like it could completely undermine your results if you get it wrong. Imagine you have a data set, maybe only 50 observations, but like 5,000 potential predictors. Think genomics, maybe finance, and you need to build a classifier. So you decide on a two-step process. First, you screen all 5,000 predictors and pick the best 100 based on correlation with the outcome. Then you fit your classifier, maybe logistic regression, using only those chosen 100. How do you estimate the true test error of that entire two-step procedure? Because you said there's a right way and a very, very wrong way.
Yes, this scenario is where things can go badly wrong, and it happens more often than you'd think. The consequences are severe. You end up with wildly optimistic performance estimates. The tempting, but completely wrong approach is this. You do the feature selection first, using all 50 observations to pick your top 100 features. Then you apply cross-validation only to the second step, the classifier fitting part, using just those 100 features.
Why does that feel natural? You've got your features, now you validate the model.
It feels natural, but it's flawed. The problem is data leakage. Or you could call it overfitting by cherry picking. When you did that initial feature selection, picking the best 100 out of 5,000, you used the outcome labels from the entire data set, all 50 observations. That means the feature selection step itself became part of the training process. You've already peeked at the outcomes for all your data before you even start cross-validating the classifier.
So you've biased the feature selection towards features that look good on this specific data set.
Exactly. With thousands of predictors, even if they're all just random noise relative to the true outcome, some will purely by chance show some correlation with the labels in your small data set. If you select those lucky features, you're building your model on features that are already overfitting to your specific data sample. You create an illusion of performance.
You had a really stark illustration of this.
Yeah. Imagine the most extreme case. Your class labels are actually completely random. No real signal. The true error rate should be 50%, right? Like a coin flip. Now, you have your 5,000 random features, you run your screening process on all 50 observations, and pick the top 100 features that happen to correlate best with those random labels. Then you apply k-fold cross-validation only to the classifier trained on those 100 cherry-picked features. What error rate do you think you might get?
Uh-oh. Something much lower than 50%.
You could get error estimates close to 0%. It looks like you have an amazing classifier, but it's built entirely on capitalizing on random chance in that initial screening step. It's a completely false, totally biased result. It tells you nothing about how that procedure would perform on genuinely new data.
Wow. Okay, that's a huge potential trap. Getting 0% error on random data is terrifying. So if that's the wrong way, what is the absolute must-follow principle here?
The ironclad principle is this. Any step that involves using the outcome labels to make decisions, whether it's selecting features, tuning parameters, whatever, must occur inside the cross-validation loop.
Inside the loop. Okay.
That means the entire procedure that you plan to apply to new data has to be repeated independently within each fold of the cross-validation.
So walk me through the correct way for that 5,000 feature example.
Okay, the correct way. First, you split your 50 observations into your k-folds, let's say 10 folds of 5 observations each. Now, for the first fold, observations 1 to 5, say, you treat that as your holdout set. Then you take the remaining 9 folds, observation 650, that's your training set for this iteration, and only using those 45 training observations, you perform the entire procedure. Step 1. You screen the 5,000 features based on correlation with the outcome, using only those 45 training observations. You pick the top 100 features based only on that training data.
Right, different features might get picked each time.
Exactly. Then step 2. You fit your classifier using only those 100 features selected in step 1, again, only using the 45 training observations. Finally, you take the classifier trained in step 2, and you evaluate its performance on the holdout fold, observations 1 to 5, using the 100 features that were selected based on the other 45 observations.
Okay.
And you repeat this whole process 10 times, once for each fold held out. Then you average the 10 error rates.
I see. So the feature selection happens fresh inside each loop, based only on the training portion for that loop. The holdout set is truly held out from all parts of the model building process.
That's the key. It ensures that the entire workflow from feature selection onwards is honestly evaluated on data it hasn't seen in any way. It prevents the leakage and gives you an unbiased estimate of how that entire procedure will perform.
That distinction is incredibly important. It's subtle, but it makes all the difference between a trustworthy result and potentially misleading one. Okay, so cross-validation is our tool for getting reliable prediction error estimates. But sometimes we want something else. We want to quantify the uncertainty around specific numbers our model gives us. Like, how sure are we about a specific coefficient? This is where the bootstrap comes in, right? And you said it's like pulling yourself up by your own bootstraps.
That's a perfect way to think about it. The bootstrap is a really flexible, very powerful statistical tool. Its main job is to quantify the uncertainty associated with an estimator or a statistical learning method. It helps us estimate things like standard errors, maybe assess bias, or compute confidence intervals for parameters we're interested in. And yes, the name famously comes from that Baron Munchausen story, the idea of generating something useful from just what you already have.
Let's make this concrete again. You had an example with an investor.
Right. Imagine you're an investor and you want to allocate your money between two assets, say stock X and stock Y, to minimize the overall risk, the variance of your portfolio. There's some optimal fraction, let's call it alpha, to put in stock X and one alpha in stock Y that minimizes this risk. This alpha depends on the variances of X and Y and their covariance.
Okay, but you don't know those true values.
Exactly. You don't know the true population variances and covariance. All you have is maybe, say, 100 weeks of historical return data for both stocks. You can calculate an estimate of alpha from that data.
But how reliable is that estimate? How much might it change if you had a different 100 weeks of data?
That's the question the bootstrap answers. In an ideal world, you'd go out and get hundreds of new independent 100-week data sets, calculate alpha for each, and see how much it varies.
Not possible in reality.
Not possible. So the core idea of the bootstrap is to mimic this process using only the one data set you have. It does this by repeatedly sampling observations from your original data set, the 100 data points. But crucially, it samples with replacement.
With replacement.
Yeah.
Meaning you can pick the same week's data multiple times in one sample.
Precisely. You create a new bootstrap data set that's the same size as your original 100 observations.
Yep.
But because you sample with replacement, some of the original weeks might appear 2, 3, or more times, and some might not appear at all in that particular bootstrap sample. You then treat this bootstrap data set as if it were a new independent sample from the population. You calculate your statistic of interest in this case, your estimate of alpha using this bootstrap data set. And you do this many, many times, say B times, where B might be 1,000 or more.
So you get 1,000 different alpha estimates.
Exactly. You get a whole distribution of 1,000 alpha estimates generated just from your original 100 data points. This distribution is incredibly useful. From it, you can calculate the standard deviation of those 1,000 alpha estimates. That standard deviation is your bootstrap standard error, SEB for alpha.
So it directly tells you about the variability, the uncertainty of your original alpha estimate.
Yes. It gives you a measure of how much that alpha estimate might fluctuate due to random sampling variation. If you plotted a histogram of those 1,000 alphas, its spread would visually represent that uncertainty. It's a remarkably clever way to estimate the standard error without needing any complex math formulas specific to that alpha calculation.
That's really neat.
It is. Now, there are some complexities. For instance, with time series data, like our stock example, simple bootstrapping might not be ideal because it breaks the time dependence. You'd maybe use something like block bootstrapping. But beyond standard errors, the bootstrap can also give you approximate confidence intervals for your parameter, like a 95% confidence interval for alpha, directly from that distribution of bootstrap estimates. For example, using the percentile method.
Okay, so Bootstrap is fantastic for understanding the uncertainty, the standard error of specific estimates. So the natural question then is, if it's so powerful, can we also use the Bootstrap for estimating prediction error, like we use cross-validation?
That's an excellent question, and it really highlights the different strengths of the two methods. While Bootstrap is brilliant for parameter uncertainty, it's generally not the preferred method for estimating prediction error in the straightforward way we discuss CV.
Why not? What's the issue?
Remember the key strength of cross-validation for prediction error. Each validation fold is completely distinct from the training folds used to build the model for that iteration. There's no overlap. That separation is really crucial for getting an unbiased estimate of how the model performs on truly unseen data.
Okay, and Bootstrap doesn't have that separation.
Exactly. Because Bootstrap samples are created by sampling with replacement from the original dataset, there's actually significant overlap between any given Bootstrap sample and the original data. On average, about 2/3, roughly 63.2% of the original data points will appear in any single Bootstrap sample.
I see.
So if you try to train a model on a Bootstrap sample and then test it on the original data points that were left out, the out-of-bag samples, or even test on the full original data set, that overlap causes problems. It means the bootstrap procedure tends to seriously underestimate the true prediction error. The model has effectively seen too much of the test data during its training phase via the bootstrap sample. Now, there are adjustments like the 0.632 bootstrap estimator designed to correct for this bias, but they add complexity. Generally speaking, for the specific task of estimating prediction error, cross-validation provides a simpler, more direct, and often more attractive approach.
Got it. So different tools for different but related jobs. CV for prediction error, Bootstrap for parameter uncertainty. What an incredible journey through how we can rigorously and honestly evaluate our predictive models. We've definitely seen that just trusting the training data. That's a recipe for disappointment, for overly optimistic results. That simple intuition needs to be checked. So to recap the big takeaways for everyone listening, cross-validation, especially k-fold, that's your go-to method for estimating test set prediction error. It helps you find that sweet spot for model complexity, balancing bias and variance, avoiding both underfitting and overfitting. And crucially, remember that any data step that uses the outcome labels like feature selection absolutely must be performed inside each cross-validation loop to avoid that dangerous data leakage and get unbiased estimates. Then, the bootstrap. That's your powerful friend for a different job, quantifying the uncertainty around your parameter estimates. It helps you understand the standard errors and find confidence intervals, giving you a sense of reliability.
That sums it up well. And if we maybe zoom out for a second, these methods, cross-validation, bootstrap, they aren't just technical tricks. They're fundamentally about building trust in the models we create. They force us to be honest with ourselves about how well our models are likely to perform before we deploy them in the real world, where decisions might depend on them. They prevent us from accidentally fooling ourselves. And this maybe raises a broader question for you to think about. In what other areas of analysis, beyond just model building, might we be unknowingly leaking information between steps? Or perhaps using evaluation methods that are too optimistic, leading us to believe our insights are stronger or more generalizable than they really are?
That is a fantastic question to ponder. Where else might we need this kind of rigorous self-checking? Thank you so much for joining us on this deep dive into resampling methods. We really hope this has equipped you with a clearer understanding and maybe a new lens to view predictive analytics through. Until next time, keep digging, keep learning, and stay curious.